This is Unit 6, Chapter 11, Learning Objective 11. This is the last learning objective for Chapter 11. Whoop, whoop. So, learning objective 11 is to solve stoichiometry problems involving reactions of gases. So, example. So, we're going to go right into an example. Seriously, Miss Cole? That's crazy. So, example, potassium chloride decomposes into oxygen and potassium chloride. It says if 1.76 grams of potassium chloride decomposes, that should say decomposes. I have terrible grammar here. Don't tell the English teachers. It says what volume of oxygen will be produced at standard temperature pressure? Whoop, whoop, we get to use the 22.4 liters. All right, so step 1, write the balanced equation. Dadgummit, I have to do this again? Yep, you do. So, potassium has a positive 1, chlorate, ClO3, has a minus 1, so KClO3. This is a solid. It's going to form oxygen. He's magnificent. He's O2, gas, plus potassium chloride. K has a plus 1 charge, Cl has a minus 1 charge, so it's KCl. And this is a solid too. So the only thing that's out of whack here is my oxygen. I have a 2 and a 3. So common multiple between 2 and 3 is 6. So I would put a 2 in front of KClO3, a 3 in front of oxygen, and then another 2 in front of KCl. Step 2. What's step 2? Step 2 is dimensional analysis. Ooh. All right, so let's go to our stoichiometry roadmap. We are given 1.76 grams of potassium chlorate. So we are here. We are a mass of potassium chlorate. We need to get to volume of oxygen at STP. So we're going to go through the molar mass of potassium chlorate to get to moles of potassium chlorate, through the molar ratio between potassium chlorate and oxygen to get to the moles of oxygen. And then we're going to get from moles of oxygen to volume of oxygen using the 22.4 liters. So we have 1, 2, 3 roads to go through. So let's set up our problem. We have 1.76 grams of KClO3 times 1 road times 2 roads times 3 roads. All right, so the first road we go through is the molar mass of potassium chlorate. If you need a reminder on how to do this, here goes. So we have to go to our lovely little reference sheet here. We need to find potassium. Potassium is right here, which is 39.10. Well, we have one of those. So 39.10 plus chlorine, which is 35.45, plus 3 times oxygen, which is 16. And that should give you 122.55, which it does. So I've got 122.55 for my molar mass. 122.55 grams, 1 mole, KClO3. And then we need to go through our mole ratio. So the moles of B, so this is A, this is B. It's going to be the moles of B over the moles of A. So I've got 3 moles of oxygen over 2 moles KClO3. So grams of KClO3 are canceling, moles of KClO3 are canceling, and then I'm going to get rid of moles of oxygen right here. So I've got 1 mole of oxygen, and that's equal to 22.4 liters of oxygen at STP. All right, and then I can calculate it. So I've got 1.76. You're going to divide by 122.55. We're going to multiply by 3. We're going to divide by 2. We're going to multiply by 22.4. And hit enter. And that gives me 0.483 liters of oxygen gas. All right, so we have seen an example of what we need to do if the substance is at standard temperature pressure, if the gas is at standard temperature pressure. However, we should know that this actually has to be heated. So there's no way that this guy is actually going to be at standard temperature pressure. So how do we solve problems that are not at standard temperature and pressure? So let's look at another example. We're using the same thing here. So we're still using the KClO3. So 2 KClO3 decomposes into 3 O2 plus 2 KCl. Potassium chlorate decomposes into oxygen and potassium chloride. If 2.26 grams of potassium chlorate decomposed, what volume of oxygen will be produced at 25 degrees Celsius and at 0.898 atmospheres? There are 2 ways to solve this problem. Both will give you the same answers. Okay, your first step for, like, if you want to do it the first way, solve for moles of oxygen first. So in this case, I'm going to take the 2.26 grams KClO3. And instead of going all the way to volume, here, like I did with this STP number, I'm just going to go through and I'm going to stop at moles of substance B. So I'm really only going through 2 rows here. So I already know the first road is 122.55 grams of KClO3 over 1 mole KClO3. And then times 2 moles, mole ratio, right? 2 moles of KClO3 over 3 moles of oxygen. And I'm going to go ahead and equal that out. So I have that number in my calculator. Okay, so I wouldn't round here if I were you. So this is 2.766 times 10 to the minus 2 moles of oxygen. So I wouldn't round that number. I would just leave it in my calculator exactly like that because I'm going to be using it in the next step. So the second step, plug your values, plug pressure, temperature, and the number of moles into PivNert. And we are solving for volume here. So we're solving for volume. So it's going to be nRT over P. So nRT over P is equal to the volume, which is equal to my moles, 2.766 times 10 to the minus 2 moles of oxygen times 0.0821. This is liters times atmospheres. That's going to be all over moles times Kelvin. And then I've got 25 plus 273 for my temperature, and that's in Kelvin. Kelvin's canceling out. Moles are canceling out. And then for my pressure, I have 0.989 atmospheres. Atmospheres are canceling out. So then plugging all this into my calculator, I'm going to take my answer that I got here. I'm going to multiply by 0.0821 times, I can close this parentheses out, plus 25 plus 273, close parentheses, and then divided by 0.898. And that gives me 0.684 liters of oxygen. So the second way that you could solve this problem is to use PV equals nRT first. So in this case, we're going to plug pressure and temperature into PV equals nRT. We're solving for V over N, and that's going to equal to RT over P. So I have V over N. This is molar volume, much like the 22.4 liters per mole is. So V over N is equal to 0.0821. This is, again, liters times atmospheres divided by mole times Kelvin. This is times your temperature, which is 25 plus 273. That's Kelvin. And then it's over 0.989 ATM. So atmospheres are canceling, Kelvin is canceling, and I'm in liters per mole. So then plugging in 0.0821 times 25 plus 273 divided by 0.898. That gives me 24.74 liters per mole. So what that means is I've got 24.7 liters is equal to 1 mole for that pressure and volume, or the pressure and temperature measurement. Your second step here is to just do dimensional analysis. So again, going back to our roadmap, we're going from mass of potassium chlorate through the molar mass of potassium chlorate to get to the moles of potassium chlorate. We're going through the mole ratio of potassium chlorate to oxygen to get to moles of oxygen. And then instead of it being 22.4 liters, we're going to have what we actually calculated in the first step, which was the 24.7 liters. Start with 2.26 grams KClO3 times 122.55 grams KClO3 over 1 mole KClO3 times the mole ratio, so 2 moles KClO3 over 3 moles oxygen, and then that is multiplied by 1 mole of oxygen on the bottom over the 24.74 liters of oxygen. Plugging all this into my calculator, 2.26 divided by 122.55 times 3 divided by 2 times my second answer gives me 0.684 liters of oxygen, which is exactly what I got at the top up here, 0.684 liters of oxygen. So again, there's 2 ways to do this, but both of the ways you're going to be using dimensional analysis and PV equals nRT. So you've got to use both of those 2 things. It's either you use dimensional analysis first to find your moles of whatever you're looking for, and then use PV equals nRT, or you're using PV equals nRT to solve for molar volume and then doing your dimensional analysis problem. Now, you always have the option of doing a BCA table. So whenever you're doing these problems, you can use your BCA table method if you want to use that. That is absolutely up to you, and it's absolutely fine to use it. So if you're very comfortable with the BCA table, you can use that. I do give limiting reactant problems, a few limiting reactant problems, and you do have to find the limiting reactant. So if you have to find that, that's going to be something that a BCA table really works well for. If you don't want to use a BCA table, don't use a BCA table. Not that big of a deal, right? This was the final learning objective in chapter 11, which was over gas laws. Solve stoichiometry problems involving reactions with gases.